In this example, we're going to solve for the moment of a force. We're going to use two different approaches. The first approach we'll use is based on Vargnon's theorem, which basically says that you can take, when you're taking the moment of a force, you can break that force into its x and y components, and that the total moment is equal to the individual moments, like in the x direction and the y direction, the sum of those two. And then we'll also use just basically like a perpendicular distance, a trig type approach. So let me go ahead and start with approach number one. And again, this is based on Fargnon's theorem. So, with Vargnon's theorem, what we're going to do is we're going to take the same drawing that we have. I'm just going to kind of simplify it a little bit here. Okay. I have this force. I'll just draw it right here. Okay, force of 25 pounds. And what I'm going to do is I'm going to break it up. Oh, let me do my moment arm. Forgot about that. Okay. I'm going to break it up into its two components, okay? So it's got a horizontal component, okay, which I'm just going to call fx. And it's got a vertical component, which I'll call fy. This angle here was given to us as 30 degrees. Alright, so in this case I can see fx is going to be equal to, based on this angle right here, fx is going to be 25 times the sine, times the cosine of 30. So I got 25 cosine 30. And then I have fy, this is going to be 25 times the sine of 30. So all I did is I took this force and I broke it up into its x and y components. Okay. And I'm going to take the moment. I'm just going to call this point right here B, for lack of a better term. So this is point B. And so when I take my moment about point B, okay, I'm going to get, let's see, we have fx. Now, if we remember on our moments, the way we designate positive and negative, we have x going to the right, positive, y going up, positive, and our moments are positive when they're counterclockwise. Okay. So, the fx at a distance of 8, so fx is just 25 cosine of 30. At a distance of 8 inches, okay, that's a positive moment, so that's why I have it this way as positive, because it's going counterclockwise relative to point B. Fy, when we look at this force, its vertical component is actually going to go down the center of this rod and right through that point. So we have no moment in terms of the y component of this because the force itself goes through that point. Okay, so the moment at point B comes out to be 173.2 pound-inches. All right, so that's using Vargnon's theorem, where it basically says we can break this force up into its component, and the total moment of this force at some distance is equal to the individual moments in the x and the y direction of the x force and the y force. Okay. Now let's look at approach number 2. Okay, and I'm just going to call this the perpendicular distance. Okay. And so what I have on the diagram shown is that if I use this idea, remember there's this principle of transmissibility, which states basically that we can look at this force along this line of action. Okay, so if we look at this force along this line of action, okay, there's a point at which we could have a perpendicular distance. So this angle here would be 90, it's orthogonal, right? And so if we look at this line of action here, there's a point in which we could take the moments about B and we could have this perpendicular distance D. Okay, so that's what I'm going to solve for now. I'm going to try to figure out what that distance D is and take advantage of the fact that I can use this principle of transmissibility. So I'm going to draw a little bit of the geometry out here just to make sure I'm square in terms of what the angles are and so forth. So right here I'm drawing this vertical piece here, which is 8 inches. Okay. So this is the force that we have, which is at 30 degrees, all right? And I'm going to just kind of draw this line out. And again, I'm after this distance D right here. Now if I just draw some other reference axes here just to kind of get an idea of what's going on, I can see, first of all, that this angle 30 has to match this angle here. Okay, so those two angles are the same. And if this angle is 30, okay, this angle here must be 90 minus 30, or 60. Okay, if this is 60 degrees and this is orthogonal, this angle here has to be 30 degrees. Okay. And that way we have a 30, 60, 90 degree. So the reason why this is important, of course, is that I want to solve for this distance D. So if I say, for example, that the cosine of 30 degrees is equal to the adjacent side over the hypotenuse, okay, that gives me a D of 6.928 inches. So now that I know this distance, I have a perpendicular distance, I know the magnitude of this force, right? This was that 25-pound force. Now when I take the moment about B, I can just use the fact that I know the perpendicular distance. Okay. So I know that perpendicular moment arm. So I've got a force of 25 pounds at a distance of 6.928 inches. And so when we take the moment based on that, surprise, surprise, we get 173.2 pound-inches. Right? This obviously is going to make me very happy because I solved the problem using two different approaches and I got the same number. Again, just to recap, I broke it down using Vargnon's theorem, where I took the force and broke it into its x and y components, and then took the moment based on that of each x and the y elements or components. The other approach that I used was to solve for the perpendicular distance based on this concept that we can use this principle of transmissibility, that the force is anywhere along this line of action. Having this perpendicular distance, we solve for the moment directly. That concludes this example of a moment of a force.